Akane, good morning. What time did you get up today? Let me guess, 11:55? Wow. Where's your cat in the box? How can this be a good morning without the cat in the box? Oh, there it is. You beat me to it. Where is it? It's this one. How do I send it? Ah. What's this? I want the YouTube symbol. No. There. Here we go. The famous cat in the box. Whew. So, what do you think next year? Is it going to be remote learning again, or are we going to be in class? I know you're not going to be in Bronx Science, but what are your thoughts there? You think we got remote learning, or we got the other thingy? Hey, Zoe. Hey, Zoe, did they say anything about Harvard being remote learning next year, or is it going to be in-person class sessions next year? Princeton hasn't said anything yet. Yeah, I think a lot of the Ivy League schools said the same thing. We were having a discussion with the physics department or the physical science department at Bronx Science, and they're thinking, I know you guys aren't going to be here next year, but they're thinking that next year we might have like some hybrid thing for the first half of the year where like some students come in, some students don't, and then they alternate or something like that. It's going to be weird. It's going to be weird. All right. So I bought this shirt in Thailand. What to focus on? Being happy. So let's begin. Let us start. Really quickly, we'll do a practice question. But before we do the practice section, let me just remind you just from yesterday what we were talking about. We were talking about the divergence of something. The divergence is given by this equation here. Some vector v times that. And from here, you're going to have three different situations. You can have the divergence greater than 0. You can have the divergence less than 0. Or you can have the divergence equal to 0. So if it's greater than 0, if you've got a field going in all different directions, let me turn off the fan. Okay, now I got to close the window. They're always doing construction. So let's say you look at some arbitrary point in space, and we're just going to look around the x direction here. If the divergence is greater than 0, that means the field lines that are going in are going to be less than the field lines coming out from this little tiny box. And then you could think of these little vectors all over here. We're just looking at a specific point. If the divergence is less than 0, then you make your little box. Again, a little point there. And then if it's less than 0, then the divergence going in is going to be less than the divergence coming out. And finally, or not the divergence, the field lines. And if you have the divergence equal to 0, then the field lines going in are equal to the field lines going out. And so that's all divergence is. Another way you could think about it is like we tend no, I'll get to that later. We'll talk about that afterwards. Let's do an example of the divergence now. So the example I want you to try is this. We're given that v as a function of xy is equal to xy in the x direction, and we have y squared minus x like that. So there's my vector, and I'll zoom into it a little bit if you can't see it. And what I want you to do is tell me what the divergence is, or what the divergence is, and then tell me whether it's going to be positive or negative at y equals and x equals and so on. So first figure out what the divergence is going to be. That shouldn't be too bad. And then somebody can write it down. Just a few more seconds. If somebody's got it, they can put it down. Okay, 3y. 3y is correct. So let me just quickly work it out, and that way everybody's on the same page. So we've got the divergence of this. That's equal to d parentheses the first term, which is xy with respect to dx, plus the second term, d of y squared minus x squared with respect to dy. That was the equation. You do the first thing, partial derivative, and then you take the second thing, partial derivative. And you're going to end up with y plus, that's the derivative of that, 2y, and you get 3y. Good. So what does this tell us? This actually is telling us something really important. We couldn't actually, by looking at, like if I was to draw the vector field lines for this right here, I wouldn't be able to get as much as by looking at this equation right here. What it's telling me is that divergence only depends on y. So it only matters if we draw our coordinate system, what the y values are. So the divergence, let's say here, whatever we get is going to be the same as the divergence here because they have the same y value. The divergence here will be the same as the divergence here because they have the same y value. So it only depends on y in this problem right here. Let's just use some examples here. So if at y equals 0, the divergence is equal to 0. That means no field lines or I guess the field lines that are coming in and out are going to be exactly the same. So it doesn't matter what x value it is. It could be 1, 0. It could be 0, 0. It could be 5, 0. Anything that has y equals 0 is going to have the same divergence of 0. And then we could do the same thing at 9. So if y were to equal 3, you end up with a divergence. 3 times this is going to be 9. And that's positive. So that means if I graph, and this is y equals 9 right here. That's y equals 9. Oops. That's y equals 9. If I chose a point right here, and I made a little box, that would say, I don't know what direction it is, but what I do know is that because it's positive, the field lines that are going in have to be less than the field lines going out. And over here, this is another y equals 9, but it has a different x value. The field line going in has to be less than the field line going out from that point. So no matter what you do in the x, as long as the y stays consistent, according to this, at least this problem right here, the divergence only depends on y, not on x. Okay? So that's that. Let us now talk about Maxwell's equations in the differential forms. I'm going to show you how we get to 2 of them today, and then tomorrow we will do some practice problems with divergence and electric fields and magnetic fields. And then on Monday, we will talk about the curl or Stokes theorem, which is part of the curl. So our first Maxwell equation was Gauss's law, E dot dA equals Q enclosed over epsilon naught. There is a differential form of this as well. And we can get the differential form by using divergence theorem, but I'll show you that later. I'm just going to tell you what the differential form is. So the differential form of this equation is going to be del dot E is equal to the charge density, that's rho, over epsilon naught. So this right here is Gauss's law. It's the same as this, just written in the differential form versus the integral form. Then our second Maxwell equation was Gauss's law for the magnetic field, and that was equal to 0. So what does the differential form of Gauss's law look like for the magnetic field? It's going to be del operator times B is equal to 0. That's not so bad. Okay. Then we can keep going. We have the, not Amperes law. Whose law is this? I forget. I'm forgetting. Somebody's law. But it went something like this. Whoops, sorry. Lenz's law, Faraday's, that's who it was. So the integral of E ds is equal to the change in the flux magnetic dt. So that was his form right there. What does the differential form look like? It looks a lot nicer than this. It's going to be the del operator, but this time it's going to be cross E. And that is going to equal negative the partial of the magnetic field divided by the time, with respect to time. Okay? And then finally, I don't even know if I'm going to be able to write this down, but I'll try. So we've got the Amperes law, B dot ds is equal to, now Amperes law had the 2 parts to it. So we're going to write it as mu naught I enclosed plus mu naught epsilon naught, the change in the electric flux over time. Yeah. And the Maxwell differential equation of this, or the differential form, not differential equation, is going to be the cross of the magnetic field, which is going to equal mu naught. Now, instead of current, it's going to be the current density, J. So J plus 1 over C squared. And then we got the partial of the electric field as a function of time, T. Where 1 over C squared, if you forgot, 1 over C squared is the same as, C is equal to 1 over the square root of mu naught C naught. And I'll write that, where C was equal to 1 over the square root of mu naught epsilon naught. So we're going to do that, something like that over there. Okay, so those are Maxwell's equations. And I'll tell you, a lot of times, they're typically like written like this. They're written in the differential form rather than the integral form. And I could show you that right here. You know, I've got this book. Every person that majors in physics will probably go through this book. It doesn't matter if you go to Harvard or if you go to some state school or something. Anybody that majors in physics as an undergrad has to go through this book right here. And look what they have right there as their front cover. They have the cross product, or the curl of the electric field and the magnetic field. So it's an important thing. They have two of Maxwell's equations written like that. Okay, so this is it. We're going to spend today and tomorrow looking at these two. And then on Monday, we'll look at the curl, and I'll show you what the curl means. I mean, some of you already know, but I'll show it to you anyways, and then we'll do Stokes' theorem, and we'll go from there. Today, what I want to do, if you don't mind, I erase this. Today, what I would like to do is show you the divergence theorem and how we get the differential form. So to do that, I pre-wrote. You don't think I work, huh? Look at that. Look at this beauty right here that I made ahead of time. So here is the divergence theorem. If you need to, you can copy it, although obviously you're not going to have the refined artistic, what's the word I'm looking for here? Aesthetics that I put down here. You know, it's not going to be as aesthetically appealing if you draw this out, but you know, give it a shot. We've got a box here, and here is the divergence theorem. It states that the integral of the surface for some vector, this isn't volume, this is some vector, is going to equal the volume of the divergence of that vector. And so what are we talking about here? The divergence just means the number of like, well, the divergence means the stuff going in versus out, and you're just adding it all together in a three-dimensional volume. Over here, this is just Gauss's law. We've seen this before. So don't be scared about this equation right here. What this is saying, if we think about it in terms of Gauss's law, is that each of these surfaces, this is a surface, this is a surface, this is a surface, is going to have some field lines coming out of it, or flux, as we say, right? So the way I write it down is that this really means the flow out through the surface. In this example here, we've got 6 surfaces. We've got surface 1, 2, 3, 4, 5, 6, 7, or 6. And that's equal to the volume of the source. And if we talk about it in terms of physics, this part right here is just the density, or the charge enclosed. That's what this part is equal to. This is the divergence theorem here. So go ahead and write it down. This is the surface integral enclosed, and this is the volume. Okay? So once you have that down, go ahead and draw out this picture here. This is a unit cube, meaning that each side has a length of 1. And we've got this vector here. I'll zoom into it so you can see a little bit better. We have the vector is equal to y squared in the I hat plus 2xy plus z squared in the y hat plus 2yz in the k hat or z hat direction. And this is a unit cube with one of the corners at the origin. Okay? Hey, Helen. And for today's lesson, I'm going to show you that this equation right here is equal to this equation right here. So that's what we're going to do. We're going to be given this. This is our, you could think of this as sort of like your electric field, and this as your surface here. And we're going to show that this is, in fact, equal to that. So this is the divergence theorem. Sometimes it's called Gauss's theorem because, you know, it was worked out by Gauss, I guess. But it's also Gauss's law. How many of you knew that Gauss's law was just a divergence theorem? I bet you didn't. I'm kidding. So, what do we want to do first? Today is a little bit of math here. Perna students know that? Okay, good. So, the first thing I'm going to do is I'm going to work out this side first, the volume. Yeah, because the volume is actually really easy to do in this situation, which is why it's going to be important that we sometimes use the differential of Maxwell's equations versus the integral. So there are benefits to using one over the other. It's not like, oh, I could use this one or that one. I mean, you could, but sometimes it's easier to use the differential form versus the integral form. So that's the motivation for why we have two. So here we go. We're going to work this out first. And I'll do that over here. Oh, surface integrals or volume integrals. This is a triple integral. I don't know if you knew that, but I purposely used the square one because I hate doing triple integrals. One just little thing that I used to do, I don't know if it'll help you or not, is I never evaluated triple integrals by making this drawing. I would normally evaluate a triple integral by looking at 3 different planes: the xy plane, the yz plane, and the xz plane. And then from that, I think the hardest part of a triple integral, in my opinion, is not actually working it out. It's coming up with the limits of integration. So by looking at it at 3 different planes, for me at least, it's easy to work out what the answer would be, or like set up the equation. But if you can do it that way, you're smarter than me. Okay, so the first thing we need to do is figure out what the divergence is, and then we'll put it into our triple integral. So the divergence, oops, that's not a delta. Delta V dot V will equal the derivative with respect to x, the derivative with respect to y, the derivative with respect to z. That's what we're doing. So the first part is just going to be y squared, right? Plus, am I saying that right? Yeah, I think I'm saying that right. I think I'm saying that right. So no. I'm saying that wrong. So if I take the derivative of this with respect to x, well, there's no x here. So the first term is 0. There we go. plus. Now, this second term I have to take with respect to y. So I see a y here. This is going to become 2x. But the z goes to 0 because the derivative with respect to y of z is going to be 0. And then we take the derivative of this with respect to z, and that's going to be 2y. So what we end up with is 2 parentheses x plus y. So there is our divergence. And now we are going to put it into our triple integral. So how am I going to write that down? This will be a good review for some of you. We've got the volume. That's not enclosed. It's just volume. The volume of my surface integral, which is going to be 2 parentheses x plus y dv. And this is a volume integral, so I'm going to put a little v there. So how do I write that as a triple integral? I would write that as, I'll write over here, equals, I'm going to pull out the 2 because it's a constant, and then I'm going to put 3 integrals, 1, 2, 3, and then this is my function here, x plus y, and then because it's volume, we're going to look at it in rectangular coordinate systems, so that's nice. It'll be dx, dy, dz. And I hope you understand why I chose the unit cube, because when we're looking at the unit cube, all of our limits of integration are going to go from 0 to 1, from 0 to 1, and from 0 to 1. So each one of these is going to go from 0 to 1, 0 to 1, 0 to 1. Okay? And so what do? We're going to evaluate this term first. And then whatever the answer there is, we're going to put it into this integral. And then whatever the answer there is, we're going to put it into that integral. Okay? So this is the first part, the second part, the third part. Let's look at the first part. To evaluate that integral, you're going to go from 0 to 1. Can't see that. There we go. We're going to go from 0 to 1 of x plus y dx. And so when you evaluate this integral right here, you are going to get 1/2 plus y. So then we take this part of the integral and we put it into the dy form. So it's going to be the integral from 0 to 1 of 1/2 plus y dy. And when we do that, we're going to get 1 as our answer. And then finally, we take this 1 and we put it into the last part of the integral. And it's going to be from 0 to 1 of 1 times dz. And that's equal to 1. So our final answer from this triple integral is just 1. And what do we do with that? So I'm going to take this 1 right here. That was my final answer. That's what this part was equal to. Inside my integrals, I can say all of that just becomes 1, but we have the 2 from the outside. So what we can say is that the volume is equal to 2. And where am I going to write that? I'll put it over here, just so we have it. So the integral, keep writing enclosed, the of d dot v dv was equal to 2. So that's what we got there. So if that's 2, we have to show that this side is also equal to 2. If this side is equal to 2, we've kind of proved by demonstration, I guess. I don't know what math terms that they use, QED, not QED, but something. We'll prove by example. I'll call it that. Okay. That was actually the easy way to solve it. All right. If you want the more difficult way, you have to solve it using the surface. What's the problem here is that we got 6 surfaces. That means we have to integrate six times. We have to integrate 6 times, and then we have to find the flux here, and then we have to add to it the flux here, and we have to add to it the flux here, and we have to add to the flux on that side, and on this side, and on the back side. And when we add up all those fluxes, that's the enclosed part. So when you see that little circle in the integral, what that means is you're adding up all of the surfaces that make up the shape right here. So we have to find each one of these shapes. Let's do it. Let's go to the front face right here. This is the front face. How do we write the integral down? Okay. Now in the front face, let me just make sure I have it, so that way we're all following along. In the front face, we are in the y and z plane. This right here is in the yz plane, and it's going from 0, x equals 0 to x equals 1 right here. So this box right here is in the yz plane, which means our vector, where's our vector right here? If we are in the yz plane, we don't care about this and we don't care about this. The x component is perpendicular to the yz plane right here, okay? So the field lines that are coming out this way, and then there's one on the backside going that way, okay? So what we want to do is we want to integrate this. The surface area is this, but the only flux that we're interested in, or the only vector we're interested in, is this part right here, because the y and z is the plane that we're looking at, and it's perpendicular. All right, so let's work it out. The first one is going to be the integral of the vector dA, and it's going to equal the double integral, because it's surface area we're talking about. We're going from 0 to 1, 0 to 1, and we're going to put just the y squared here because we are integrating with respect to y and z. So y and z is the surface, and the x part of my function is the thing that's going perpendicular to it. Okay? So when you work this out, you're going to get 1/3. And then we do the same thing again. So this was our first surface. Let's put numbers on them too. So this was surface 1. Then we're going to look at the next surface, which is 2 VdA, and that's going to equal the integral of 0, 0, 1, 1, y squared again, dy dz, except we're going to have a negative here, because if you look at surface 2, this is surface 1. Surface 2 is the back surface, and the back surface is pointing in the opposite direction. This vector is going that way. This vector is going that way. So we have to put a negative sign here. So it's negative this. And when you do that, you will get negative 1/3. Okay. The next surface is going to be surface 3. 1, 2, 3. And it's going to be V times dA, just like we did. Now for this one, what are we going to have? We are going to be looking at surface 3. Let's go to our picture here. Surface 3 is this part right here. It's 3 going that way. So for surface 3, we are in the x and z plane. We're moving in the x plane and the z plane. So this surface is the xz plane, which means we don't care about the x hat and we don't care about the z hat. We're only concerned about this term right here. So what do we get? We are going to get the double integral from 0 to 1 of this function here, this part of the function. And I'm going to do something, and I hope you understand why I'm going to do it. I'm going to write as 2x, but I'm not going to put the y there, plus z squared dx dz. So it should be 2xy plus z squared. Now, why am I not putting the y term here? Because this is evaluated at y equals 1. If we go to our picture here, this plate right here, look at this plate right here, this side of the plate. It's at y equals 1. So I'm not going to put y here. I'm just going to put 1 there. Whew. So we do that, and we're going to get negative 1/3. Okay, we're halfway done. Whoa, we're halfway there. Okay, so we have 1/3, negative 1/3, negative 1/3. I'm going to keep track of all of these, so that way I don't have to, I could erase this board here. So where am I going to put that? I'll put it right here. We've got 1/3 minus 1/3 minus 1/3. Let's erase this and continue on. So the next surface that we're dealing with, VDA, this is vector, is going to be surface 4, and that's going to equal the double integral. I'm going to put a negative sign in the beginning because this is going the opposite direction now, from 0, 0, 1, 1. And then what are we going to put in here? We're going to put the y component, except this time, this 2xy is all going to 0 because we're looking at this surface right here. I guess it's the left side, not the middle, but this side right here. This side right there. I don't know if I can show you that better. So at this side right here, y is equal to 0. So this surface on this corner right here is equal to y equals 0. So then we just substitute 0 into here. And then what we're going to put in our integral is just going to be z squared dx dz. And make sure you have the negative sign because the surface integral 4 is going in the opposite direction. So we do that, and we can integrate this. What are we going to get? Oh, I messed up somewhere. This should have been not negative 4/3. Surface integral 3 was plus 4/3. Sorry about that. So the answer to this integral, like the surface area going that way, was 4/3. And the answer to this one was negative 1/3. Apologies. So we'll put the negative 1/3 there. All right. And if you tried that already and you were confused by it, I apologize for that. So if we go back to surface 3, which was right here, and you evaluate it, you're going to get 4/3, not negative 1/3. It's surface 4 that's negative 1/3. Okay. Lastly, hopefully you've got the idea down of how we evaluate all these integrals. We can do the, oops, I don't know if you'd see that. The volume of 5 is equal to from 0 to 1, 1. And we are now looking, we did the, what term are we looking at now? XY. So the 1 through 4 all had dz terms in them. And now we're looking at the top plate right here and the bottom plate. And in the top and the bottom plate, those are in the xy plane. So there's no z component there. So if it's in the x and y plane, then the component that's perpendicular to the xy plane is the z component. So we're looking at 2yz. And once again, if you look at the top plate right here, this top plate, the top plate is when z is equal to 1. So we have 2y times z, but z is equal to 1 at the top plate. So we really have just 2y. And I'll write that as 2y dx dy, and we can evaluate that integral. We will get, and I promise you this time, we will get 1. And finally, the last one, which is going to be surface area 6, which is going to be that, and that's equal to the double integral. It's going to be negative because it's pointing down. And down we're going to assume to be the negative direction. And what are we going to put there? Well, at the bottom plate right here, z is equal to 0. So if I plug that into this part right here, it's going to be 2 times y times 0. So that is 0. dx dy. And all of that, well, when you take the integral of 0, it doesn't matter how many times you take the integral of 0, it's still going to be 0. So let's put it all together. We've got 1/3 here, minus 1/3, plus 4/3, minus 1, plus 1, that was surface area 5, plus 0. You add them together, you get 2. And that's what we expected to get. So we can say that the surface integral of the vector v dA for the surface is also equal to 2. And so this shows you that the divergence theorem, this is the definition of the divergence theorem, works out, because what you have here is equal to what you have there. Whew. Now let's put that into Maxwell's equations, this divergence theorem. Hopefully I've shown you that this is true, and now we can actually put it into our equation and see what happens. So we're going to transform the integral to a differential form. How are we going to do that? Let's see here. We're trying to show this, that is equal to the density over epsilon naught, and it is the differential form of this. I want to go and put the enclosed surface, yeah. Surface EDA equals Q enclosed over epsilon naught. Okay? And one thing you want to remember is that Q enclosed, if you forgot, is really just the density equation of the volume, rho dV. So that's what Q enclosed is equal to. Okay, so let's use the divergence theorem. The divergence theorem states, with electric fields in there now, the volume, or the surface of the electric field, EDA, is equal to the volume of this cross E dV. Okay? So that's what the divergence theorem states. Now, this part right here is equal to Q enclosed over epsilon naught. So remember, this is equal to Q enclosed over epsilon naught. And Q enclosed is equal to this term right here. So on this side, I'm going to put down the integral V rho dV over epsilon naught. So this becomes that. And on this side, we have volume thank you. Dot. Thank you. Yeah. So there we go. And so over here, we get the, I'm just going to rewrite that, electric field times that. So I substituted for here, and I've left this side alone here. Well, look at this. You have a volume, and you have a volume integral. We can get rid of those volume integrals on each side, and we're left with rho over epsilon naught is equal to the divergence of the electric field. And there it is. So using the divergence theorem, we can come up with the differential form of the electric field. So the divergence is equal to the density, not the charge enclosed, but the total density divided by epsilon naught. And tomorrow we will look at examples of using this equation right here. So I think that's a lot of enough math for today. Yeah, I think that should be good for today. We'll stop it there, and we'll look at some problems tomorrow. What are we going to do after this? Monday we'll do the Curl and Stokes theorem. We'll start that, and we'll do the cross product stuff. And is there anything else? Oh, we have to decide what it is you want me to cover. There's three things. I'll let you think about it for now. We can go into optics, which is pretty cool. There's a lot of things we can talk about optics. Fluids, we're going to have to learn even more math because you have to learn this thing called the Laplacian. And we have advanced mechanics. So in advanced mechanics, I'll show you what real math looks like in physics. You'll learn this term called the Lagrangian operator and the Hamiltonian operator. And you'll do some really intensive math stuff, which I think most of you, at least the people that are on here, you guys are all capable of doing. It's very long in terms of mathematics, but it's pretty cool once you get the idea of it. I wish I knew how to do it when I was in college in the first year. But that's it for today. I will see you tomorrow. Adios. Adios. See ya. See ya, cowboy, or adios, cowboy. I forget. Whoop. See you, Zoe. Akane, see ya. Yeehaw. Oh my goodness. All right, I'm out.